Now I just want to quickly take our equation of motion for an object sliding down a plane under the force of friction and look at a couple of limiting cases. So the first limiting case that we're going to look at is the case where we see if this equation could also describe an object sliding along a horizontal plane. Now why do we call that a limiting case? Limiting case 1 is that theta tends to 0, which would be the case if instead of a slope we had a flat horizontal plane. So let's look at this equation here for our acceleration and find out what it becomes if theta equals 0. So now we can write that the acceleration equals g sine of 0 minus mu k cos 0. Sine of 0, 0, cosine of 0 is 1, so this gives us minus g mu k. So that's the acceleration of an object sliding along a horizontal plane with the only force on it being the force of friction. We see that the force and the acceleration therefore are in the direction opposite the motion, and we see the expression for the size of that acceleration is simply minus g mu k. Now we're going to look at limiting case number 2. Limiting case 2 is, well, what happens if we simply ask for the equation of constant velocity? Now, how is that a limiting case? Well, that's a limiting case because constant velocity implies a equals 0. So we can take our equation again for acceleration and set it equal to 0 this time. So we have 0 equal g sine theta minus mu k cos theta. This is for the sloping case again. And obviously we can see from this that g sine theta equals mu k g cos theta. And we see the number of things cancel. Interestingly, the acceleration due to gravity drops right out of this thing, and we end up with mu k equals sine theta over cosine theta, which equals, of course, tan theta. So in the end, this is the expression linking the coefficient of kinetic friction and the angle of the slope for an object sliding at constant velocity. And we see that these two limiting cases both came naturally out of the full solution for the object sliding down the plane with friction.